call that area equals to double integral of 1 dA, right? So what you can do here is you can pretend that U1 is your either partial derivative of, so there are two possibilities now. You can pretend that U1 is your partial derivative of Q with respect to X. So if you do that, then you can find Q is going to be equals to X. So if Q equals to X, we're going to get that equals to X dy using the Green's theorem. Because if you know what X equals to Q, that's what you get. Or you can pretend that 1 equals to negative dp over dy, then you get p equals to negative y. So you can also get, if you want, c negative y dx. And if you want to get a bit more of that, then you can take average of these two. So you might say 1/2 integral c x I minus y dx. Okay. So you can calculate area using our line integrals. Say we have ellipse, and we want to find its area. Okay, so we have double integral of 1 dA, that's area. Okay, and say we've decided to do, let's have a look. I guess this one, because it has positive. That's the only reason, I guess. So by Greens, that is c x dy. And now our parameterization for that ellipse is going to be x equals to a cosine theta, y equals to b sine theta. Theta is full circle from 0 to 2 pi. So do substitution. So we're going to get integral 0 to 2 pi. X is a cosine theta. Y is b sine theta. So find dy. So we're going to get b cosine theta, d theta. So we're going to get AB 0 to 2 pi cosine theta squared d theta. Recall what is antiderivative of cosine theta squared. So we're going to get AB times, say, cosine reduction formula for integrals. So cosine theta sine theta over 2 plus theta over 2. We're doing it from 0 to 2 pi. Substituting 0 and 2 pi. Sine of 0, sine of 2 pi equals 0, so it disappears. Substituting it for phi for theta, we're going to get AB times pi. So that's this example. So we have our region D, right? And what we do is we assume that we have like fluid which is flowing through that region, right? So we have fluid which is going through that region, right? Okay. Maybe with some swirling a little bit here, a little bit there. Okay. So what we have here, if you like, the ones which are coming in, that's going to be inflow. And the ones which is going to be coming out, that's going to be outflow. Okay. And flux is going to be equal to total net mass of fluid, which is inflow minus outflow. So total net mass of fluid leaving region D. Okay. So if something leave it, we calculate this positive. Something coming in, we calculate this negative. So outflow minus inflow. So let's do the calculations here. So as usually what we'll do, we'll divide the whole thing into small pieces, right? Like we usually do. We'll divide the whole thing into small pieces. Right? And then we're going to pay attention only to a small piece. So let's have a look what's going to be happening on a small piece. Okay. So we have our normal vector here. Okay. Let's use little. And then we have our fluid given by vector f, which is going to have m and n coordinates. Okay. Then over that piece, outflow over that small piece is going to be approximately equal. So what we do is we multiply, we will do project f on normal vector, and then we multiply by how much area length we will have. So we take, to find the projection, we take dot product between normal vector and function, and we're going to multiply it by how much area, in this case length, we have. Okay? So fi times ni will project it into here. That part will be fi times ni, the magnitude of that perpendicular piece, parallel to normal vector. And then we multiply it by how much we have. We're basically calculating that rectangle, and that's how much fluid outflow we have. So then we adding them up together. So flux approximately is going to be equal to sum fi and I delta s, I from 1 to n. And if I move on to the next page, I'm going to get flux. It's going to be equal to closed integral. So we're taking limit as number of segments approaching infinity. So we're going to get whole integral. So we're going to have f times n ds. Okay. Now let's recall what's going on. Recall what is happening is, what is our usual setup is when we have FDR, we have F times TDS, right? We have TDS. where t here is going to be, so we have unit vector in direction of velocity. So we have dx and dy, and we taken it ds dy, right? Oh, sorry, ds dy ds. Because we are talking about two-dimensional case, we can easily find what will be normal perpendicular vector to two-dimensional vector. So basically you flip the coordinates and put minus. So n is going to be equal to, we flip them, and we're going to put minus. And I put in minus for dx because I want it to be leaving the curve. Leaving, okay? So that's what n is. And if you know what n is, we substitute it in here, we're going to get integral f is m and n, right? F is m and n is dy negative dx. Yes, 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 simplified. So we're going to get ds will be cancelled out. Distribute multiplication, dot product. So we're going to get c negative n dx plus m dy. So that's flux. Okay, so that's two-dimensional flux. And then we can, from here, we can get Green theorem for flux. 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 Let's close to the C. And yes, equals to double integral r partial derivative m x plus partial derivative which equals to gradient of f t where